Hello everyone. This presentation is on deadlock avoidance. In this presentation, we will discuss methods to prevent deadlocks in operating systems. The two main topics that we will cover are, first, Resource Allocation Graph, which is a directed graph that describes resource allocation among processes, and second, the banker's algorithm, a deadlock avoidance algorithm that tests for safety by simulating resource allocation. Let's start by understanding what a deadlock is. A deadlock occurs when a set of processes are blocked because each process is holding a resource and waiting for another resource that is already acquired by some other process. There are four necessary conditions for a deadlock to occur. These are: first, mutual exclusion, which means that resources cannot be shared; second, hold and wait, meaning processes hold resources while waiting for others; third, no preemption, where resources cannot be forcibly taken away from a process; and fourth, circular wait, which means there is a circular chain of waiting processes. The diagram illustrates a circular deadlock scenario, where four processes, P1, P2, P3, and P4, are each waiting for a resource held by the next process in the circle. Now let's discuss the Resource Allocation Graph, often called RAG. This is a directed graph used to represent the state of a system in terms of processes and resources. The components of a RAG are processes, represented as circles; resources, represented as squares; request edges, which are directed from process to resource; and assignment edges, directed from resource to process. A RAG can be used for deadlock detection. If the graph contains a cycle, a deadlock may exist in the system. For single-instance resources, a cycle always indicates a deadlock. The diagram shows a resource allocation graph with processes P1, P2, P3, and P4, and resources R1, R2, R3, and R4. Request and assignment edges show the allocation and requests of resources among the processes. Also included is a key that shows what the shapes and lines represent. Circles are processes, squares are resources, dashed lines represent a request, and solid lines represent an assignment. Now let's talk about deadlock detection using the Resource Allocation Graph. For single-instance resources, if the RAG contains a cycle, a deadlock exists. We can use cycle detection algorithms to identify these deadlocks. For multiple instances of a resource, a cycle is a necessary but not sufficient condition for a deadlock. In such cases, we need additional analysis, such as the banker's algorithm. In the diagram, there is a cycle involving processes and resources. The cycle is highlighted with a dashed red line, indicating a deadlock is present. The words cycle detected and deadlock present are written in red on the figure to further emphasize that fact. Let's delve into the banker's algorithm. This is a deadlock avoidance algorithm that tests if a state is safe by simulating resource allocation. Key concepts include a safe state, where the system can allocate resources to each process in some order without causing a deadlock; an unsafe state, where there is no guarantee that resources can be allocated without a deadlock; and a safe sequence, which is an order in which processes can complete without causing a deadlock. The banker's algorithm operates under certain assumptions. Maximum resource needs are declared in advance, processes release resources voluntarily, and when a process gets all its resources, it must return them in a finite time. The diagram illustrates safe and unsafe states with a current state indicator and arrows showing possible transitions. Safe states are highlighted in blue, and unsafe states in red. To implement the banker's algorithm, we need to understand the key data structures it uses. For n processes and m resource types, we have available, a vector of length m, where available j equals the number of available instances of resource type j; max, an n by m matrix, where max I, j equals the maximum demand of process I for resource j; allocation, an n by m matrix, where allocation I, j equals the number of resources of type j allocated to process I; and need, an n by m matrix, where need I, j equals the remaining resource need of process I, calculated as max I, j minus allocation I, j. To illustrate, we have an example data. The available resources are 3 of resource A, 3 of resource B, and 2 of resource C. The allocation matrix shows the current allocation of resources to each process P0 through P4. For example, P0 has 0 of A, 1 of B, and 0 of C. The safety algorithm is crucial for determining if a system is in a safe state. We initialize work to be equal to available, which represents the available resources. We also initialize finish I to false for all processes. Then we find an unfinished process I where finish I is false, and need I is less than or equal to work. If such a process is found, we assume it can complete. We update work by adding allocation I, and set finish I to true. If finish I is true for all I, the system is in a safe state. Otherwise, it is in an unsafe state. This algorithm is further explained as follows. First, initialize the work and finish arrays. Second, find a process that can complete with the current resources. Third, update the state when a process completes and releases its resources. Fourth, repeat until all processes complete or no eligible process is found. Fifth, check if all processes finish to determine safety. If the algorithm succeeds, the order in which processes were selected forms a safe sequence such as P1, P3, P4, P0, P2. Let's now discuss the resource request algorithm. When process P sub I requests resources, denoted as request sub I, we follow these steps. First, if request sub I is greater than need sub I, return an error because the process exceeds its maximum claim. Second, if request sub I is greater than available, the process must wait as resources are unavailable. Otherwise, we proceed with a tentative allocation. We pretend to allocate resources to P sub I, update available by subtracting request sub I, update allocation sub I by adding request sub I, and update need sub I by subtracting request sub I. Then we check if the resulting state is safe using the safety algorithm. If the state is safe, the allocation can proceed. Otherwise, we restore the original state, add request sub I back to available, subtract request sub I from allocation sub I, add request sub I back to need sub I, and make the process wait. The resource request process includes validating the request, tentative allocation, safety check, and making a final decision based on the safety check. It's important to note that this algorithm is conservative. It denies requests that might lead to a deadlock, even if they might not actually cause one. Now let's walk through an example to illustrate how the banker's algorithm works. Consider the current system state with the given allocation matrix showing how much of resources A, B, and C are allocated to processes P0 through P4. The available resources are 3 of A, 3 of B, and 2 of C. Executing the safety algorithm, we initialize work to be equal to 3, 3, 2, and finish to be equal to false for all processes. We then find a process where finish I is false and need I is less than or equal to work. A safe sequence is found, which is P1, P3, P4, P0, P2. This is because P1 completes releases 2, 0, 0, and work becomes 5, 3, 2. P3 completes releases 2, 1, 1, and work becomes 7, 4, 3. P4 completes releases 0, 0, 2, and work becomes 7, 4, 5. P0 completes releases 0, 1, 0, and work becomes 7, 5, 5. Finally, P2 completes releases 3, 0, 2, and work becomes 10, 5, 7. Since all processes can finish, the system is in a safe state. To summarize, the key takeaways from our discussion on deadlock avoidance are: the resource allocation graph helps visualize and detect potential deadlocks. The banker's algorithm ensures the system remains in a safe state. The safety algorithm determines if a state is safe by finding a safe sequence. And the resource request algorithm decides whether to grant resource requests. However, deadlock avoidance techniques also have their limitations. The advantages of deadlock avoidance are no need to preempt and rollback processes, guarantees deadlock prevention, and allows higher resource utilization than prevention. The disadvantages are that it requires knowing maximum resource needs in advance, the process population must be fixed, and resources must be released voluntarily. In real-world applications, deadlock avoidance is used in database transaction management, operating system resource allocation, cloud computing resource scheduling, and distributed systems coordination. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.